Welcome back to my channel. Today we're going to be talking about integration by parts. Uh, and we'll talk about what that is, when we use it, things like that. So when we run into problems like x times sine of x, our first immediate thought is going to be, let's try u substitution. So looking at this, we kind of have two options here. If I were to make u equal to x, that means du would equal dx. This is going to change our integral to, instead of x, we now have u, sine of u du. And if we look at this here, that did literally nothing for our problem. We have now just changed x's to u's, and it's the exact same problem. It's not any easier. Okay, our other option here is, let's make u sine of x. So if I make u sine of x, that's going to make du equal to cosine of x dx. Our new problem, cosine is not in this problem, so we can't really do either of these things, which means we now have to try something else. So the part of this problem that's causing us an issue is that multiplication between x and sine of x. And whenever we see multiplication with a derivative, we use product rule. So we're going to take a second and look at product rule again here. So I wrote down f of x and g of x, so we know with product rule, f prime of x times g of x plus g prime of x f of x, or f of x times g prime. Either one works. So what we're going to do is we are going to take this and we are going to integrate both sides because we want to deal with integration here. So we're going to rewrite out what we have to begin with. So we have the derivative of f of x times g of x. We know that that is equal to f prime of x times g of x plus g prime of x times f of x. So we're going to integrate everything that we have going on here. So we're going to integrate each one of these pieces. I need to add a dx to all of these to make sure that we're integrating with respect to the right variable. But that's what we would do here. I have integration and a derivative right next to each other. They are inverses of each other. If we integrate something and then take the derivative of it, we're going to get the exact same thing. So what we have here is f of x times g of x. And then we have these two integrals that we're not really going to change anything with. They are just the integral that we're going to be dealing with. The other thing I'm doing is I'm going to rewrite this so that way f of x is first. It's not necessarily needed. It just looks a little bit better. Okay, so here's the next thing. When we do what we're going to be doing, it doesn't necessarily matter which integral we pick as the one that we want our problem to start with. As we talk about in general, this is the side that we want to start with. So our problems are normally going to start with this side, so we want to get this side by itself. So in order to do that, we are going to subtract the other integral, that integral of f prime of x times g of x, to the other side. In doing so, we have f of x times g of x minus the integral of f prime of x times g of x dx equals this other integral f of x times g prime of x dx. At its core, this doesn't look like it's going to be helping us that much, but what we've done is we've gotten rid of one integral. Hopefully the other integral we have to deal with is not too bad. It's something that's manageable, and we have f of x and g of x just being multiplied together. So if we can find our functions, it makes it a lot easier. This right here is our integration by parts formula. They call it integration by parts because we're taking a part of the function, integrating it, and then it's going to lead us to the integral of a different part of our function. So we're going to change this into u's and v's because it looks a little bit nicer. It looks a little bit more compact when we use u's and v's. So we have the integral of u dv. So when we have u dv, that's the same thing as f of x g prime of x dx. The difference is all of our g prime of x dx, this is dv. This f of x is our u. This is equal to u times v minus the integral of v times du, just like in the other one. V is g of x, and du is f prime of x dx. One of the things that we have right here is a way to remember what we have together is we have a phrase that we can use for this side of our formula. And our helpful phrase is going to be ultraviolet voodoo. And yes, we spelled voodoo wrong here. So this comes from u times v du. So it's more of just to help us know which letters go where and as we're trying to do this. So when we start out, we're going to be using ultraviolet voodoo a lot. And honestly, anytime I do an integration by parts problem, I automatically think of ultraviolet voodoo. So let's look at an example of what that would look like. So just like with u substitution, we want to pick our u first. The difference being when we pick u here, we generally want it to be something easily differentiable. And dv, we want to be something easy to integrate. So we have x sine of x. Something that's really easy to take the derivative of, 1x to the first power. So we're going to make u be x. dv, we're going to make it sine of x with that dx. So we have u, we need du later on. We have dv, we need v. So when we do du, we need to take the derivative of u. Du is equal to 1 dx, or just dx. We have dv, we're going to take the integral of dv. This would give us v. The integral of sine is negative cosine. And then we're going to leave the plus c off for now because we're going to see it come back in later. So we now have these parts and pieces. We have u, v, du, and dv. So we're going to go ahead and put it into this ultraviolet voodoo formula. So as a reminder, we have the integral of u dv is equal to ultraviolet voodoo. So we have u first. So we have our integral right here. We're going to take u and multiply it by v. So we have x times negative cosine of x. We're going to subtract the integral of v, that negative cosine of x, times du. Du is equal to 1 dx. And then we are going to simplify it and then do the actual integration here. So x times negative cosine, we can rewrite this as negative x cosine of x. We have minus, we can bring that negative out front of our integral sign. When we have minus a negative, we're going to make that into a positive. So we're now adding these two together. And then we have cosine of x. We multiply it by 1, is still cosine of x, so we get the integral of cosine of x dx. We don't have to do anything with x cosine of x, but now we are going to do the integral of cosine. The integral of cosine is sine. And then because we did our integral, we're going to add plus c. So when I do that integration by parts, I'm kind of splitting up the pieces that we're dealing with to make an integral that is easier to work with. So instead of doing the integral of x times sine of x, I'm now doing the integral of cosine. So what would happen if we changed u and dv? So would that make our problem any different? Would I still be able to solve it? So we're going to change u and dv. So my u this time is going to be sine and my dv is going to be x. So u is sine of x, dv is x with that dx. So if we take the derivative of sine of x, we have cosine of x dx. If we take the integral of dv, we get v is equal to the integral of 1x to the first is x squared divided by 2, or 1/2 x to the second power. And then we have our plus c that we're going to incorporate later. So we're still going to do our ultraviolet voodoo. So u times v, so we have sine of x times x squared over 2. We can't really simplify that a lot, so we can look at it just like that, minus the integral of v du. So v in this case is x squared over 2. Du is the same thing as cosine of x dx. So looking at what we have here, this integral, even if we take out the 1/2, we have the integral of x squared times cosine of x. This is now harder than our original problem. Even though it's kind of a lot of work, the easiest way to tell which one you should use when is just by practicing it. So looking for things that are easily differentiable, x is always going to be one that we probably make u just because it goes away. Sine and cosine are kind of in this weird spot where we can kind of put it either in the derivative category or the integral category because it's easy to do both. So this is one of those things where it's just going to take some practice to kind of figure out what we have going on here. Okay, so let's look at this one. We have the integral of x squared times the natural log of x. When we look at this, u is always something we want to do the derivative of easily. dv is always something that we want to take the integral of easily. So if we look at x squared, we can take the derivative of x squared, totally fine. We can also take the integral of x squared, totally fine. Power rule is not horrible. Natural log, on the other hand, we can take the derivative of natural log, it's 1 over x, we're done. But we have never actually done the integral of just natural log of x, and there's a very specific reason for it, which we'll talk about in a little bit. So in this particular case, we want to make u, the thing we're going to do the derivative of, natural log. Anytime we see natural log, automatically going to be u, even when we have x to a power. This makes dv x squared dx. So our integral of u, 1 over x dx, the derivative of natural log is du is equal to 1 over x dx. The integral of dv, we have v is equal to add 1 to the exponent, divide by that exponent. So 1/3 x cubed, or x cubed over 3. So now we're going to do ultraviolet voodoo. So we have ultraviolet, so u times v minus the integral of v du. So we have 1 over x dx. Okay, right now this doesn't look very nice, but we're going to do some steps to try to simplify it. So we have x cubed over 3 times the natural log of x minus, I'm going to factor out the 1/3, move it out front to make it easier on our integration. And then I'm going to multiply these two fractions together. So we get x cubed over x dx. In doing that, x cubed over x can be simplified to x squared. So what we really have is x cubed over 3 times the natural log of x minus 1/3 times the integral of x squared. Well, we've already had to do the integral of x squared in this problem, so we might as well do it again. The integral of x squared, we already said was the x to the 3rd power divided by 3, or 1/3 x cubed. We did an integral, so we need to add c at the end. And then I can simplify this if I really want to, or I can leave this as is. One of the things that I realistically could simplify from everything is we have an x cubed over 3 in everything. So I'm going to go ahead and factor out x cubed over 3, and then I'm left with natural log of x minus 1/3 plus c. What it would actually look like is completely dependent on the problem, what multiple choice we're looking at, anything like that. So it just kind of depends on what we have to deal with.